In the last video we talked about velocity selectors that create streams of charged particles all going in one direction at one speed. And I said that that's usually used with other devices. And in particular, it's used in a mass spectrometer. So a mass spectrometer, the point of a mass spectrometer is to identify chemicals. So you have some unknown chemical and you put it into the machine, and it will tell you what it is based on its mass to charge ratio. So the M divided by Q. So different substances, molecules, atoms, whatever, have a particular mass, a particular charge. And usually from the ratio of the mass to the charge you can identify what it is, because different substances have specific mass to charge ratios. Okay, so how does it work? How does it know what the M divided by Q is? Alright, so you take your unknown substance. There's the substance. And you do something to it to make it eject bits of itself, charged bits of itself, and so it's going off in all directions. So now the first thing is you run this through a velocity selector as described previously. Alright, so now you know that coming out the other side they're all moving at a known speed. Okay. Now, what do you do with that now that you have this stream of particles of known speed? You run it into another magnetic field. I say another because remember the velocity selector has its own magnetic field that it used. But now we have another magnetic field. And we talked about this before. What happens when this thing goes into the magnetic field is it's going to go into a semicircular trajectory. And again, you're going to have a screen over here, and depending on whether it's positive or negative, it could also go on the other side. So you have a screen here that can detect when this thing goes in, turns around, and boom, hits the screen. You can measure the radius of the circle that was created, basically half the distance from the entry point to where it hit, right? So now you can detect the R, you can measure that R. Now we have our great relationship RQB equals MV, and we measure this, as I just said. You're in control of the B, so you set up the B, you know the B. Your velocity selector means you know the V. Alright, so let's see, if I move the V over here, the things we know, the three things I pointed to, put them on one side, and the M and the Q are on the other side. So this is all known, and so therefore you now know M over Q. So you can figure out the mass to charge ratio of your unknown substance, right? And then based on that you identify the substance that you had. So that's how a mass spectrometer works. Okay, finally, a third application is called a cyclotron. And this is an interesting thing in how it works. So this is a way of accelerating particles that have charge to really high speeds, now, of course, one way to do that doesn't require anything super fancy is to just set up a uniform electric field. We saw that in an example a little bit ago where we used an electric field that took an object, a charged particle at rest, and just accelerated it, right? Because it's just pushing it. It's just applying an electric field, an electric force because of the electric field, excuse me. So that's great. But the problem is if you want it to go really fast, you're going to need a really long distance of uniform electric field. It would need to, right? It needs to be linear. It needs to be straight, and so because electric fields are just going to make it go faster, you would need a really sort of infeasibly long stretch, basically a really long runway, to get your charged particle going as fast as you want. Now, smaller speeds, okay, you can do this, but for really, really big speeds, it's sort of not practical to make this big, 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 long runway of an electric field. Okay, so we use cyclotrons instead, which is it's basically making a circular runway. We make it go around and around and around. Let me explain how this works. So we have this circular thing, and this in here, this is a piece of metal right here, and this is a piece of metal right here, solid piece of metal. Or actually, I shouldn't say that, not necessarily solid. Sorry about that. But so what you do is a piece of metal right on this side and on this side anyway, and we hook those up to some battery, strong battery that creates a delta V. So this side will be positively charged and this side will be negatively charged. Okay, which means that you're going to have an electric field in this little gap between the two. Okay, so you take your charged particle and it starts at rest and you just put it right smack dab in the center of this thing. Now, of course, what's going to happen is, well, if it's, let's say it's positively charged, then it's going to go with the electric field. So it's going to pick up a little bit of speed and go over to this side. If it were negatively charged, it would go the other, everything would be reversed. But so it starts in the middle and it moves over. Now, once it goes past this side, it's no longer in the electric field. But now at the same time, what I haven't mentioned yet is that there's a uniform magnetic field pointing upward. And I didn't draw all the arrows throughout the whole picture because it would just be covering up the picture, but just imagine magnetic field going upward all through the whole cyclotron. Okay, so when it gets here, it has a little bit of speed. And of course, now it's in, because it's in a magnetic field, it goes in a circle. And it hasn't picked up much speed yet. So if this guy is small, then we're going to have a small radius. So it'll just be a little, maybe not even, maybe just like to there. A tiny little flip around. Now, while it was turning, what we do is we actually alternate. We change this to negative, change this to positive. So now the electric field is going the other way. So now as it crosses over the gap again, it's again going sort of in the way that's going to make it go faster. See, if we had left the arrows going the same way, any speed we picked up, when it came back around, that would have just slowed it down again. It was like going downhill, but then we're going uphill, so we're going to lose all our momentum. But that's, and this is the key of the cyclotron, you time it so that you switch it every time it crosses so that it's always going with the electric field and thereby getting faster. So it goes over here. Now it's going a little bit faster, so the radius is going to be a little bit bigger. So now it's going to go bigger circle. Then again, this is switched again, so now it's going across and it's faster, so a bigger circle. Across, so faster, and a bigger circle. And so what happens is it starts spiraling outward, and I haven't drawn this very well, but eventually, when the radius is big enough, there's going to be an outlet, and it's just going to shoot out. So basically, it accelerated a whole bunch of times. Every time it crossed this gap, it sort of encountered more delta V, and that pushed it to go faster. And it does that, many, many, many times, way more than I've actually drawn. Each time, the radius gets a little bit bigger, so it's spiraling outward and picking up speed all the time. And it, like I said, once it finally gets to the outermost radius, there's going to be a little escape hatch, and it just boom, shoots straight out. And it leaves the magnetic field, so it's no longer turning anymore, and you've got a really, really fast particle coming out of this thing. So that's called a cyclotron. So as I said, it basically, instead of having to go to pick up speed in a straight line, you do it by spiraling. And a really smart use of magnetic fields and alternating voltages. Okay.